Hello, everyone. Good morning and welcome to the CMSA Colloquium this week. Today, we are very glad to have Professor Tamas Hausel as our speaker. Professor Hausel obtained his PhD in 1998 from the University of Cambridge and has worked at AAS, UC Berkeley, UT Austin, Oxford, EPFL, and he's currently at IST Austria. His distinguished career has been marked with numerous awards, including the Whitehead Prize of the London Mathematical Society in 2008. Without further ado, let me give the stage to Professor Hausel, who will give us a talk on Hitchin map as spectrum of equivariant cohomology. So please.
Thanks very much for the invitation and the kind introduction. So I'm going to report on a recent, discovery I made, which is part of a ongoing project with Nigel Hitchin, where we are studying the Hitchin integrable system on certain upward flows in the moduli space of Higgs bundles. And the curious occurrence is that recently I managed to find in some particular examples the Hitchin map on this upward flow can be modeled as the spectrum of equivariant cohomology of some Grassmannians. So I still don't quite understand what this means, but the occurrence there is 100%. So it is there, the spectrum of equivariant cohomology inside the Hitchin map, and it's still curious to find out what this means. So let me then start the discussion and discuss first what we call in this generality very stable maps and multiplicity algebras of maps between, well, in the largest generality between affine varieties with a C star action. So the setup is this. We have two affine varieties, U and V. In this talk, everything will be over the complex numbers. We will have C star action on both of them. And the C star action on these affine varieties will be special. They will have a single fixed point, what some people call attractive C star actions, and all the weights are going to be positive of the C star action on these affine varieties. You will see that it fits very nicely into the general framework of what I call semi-projective varieties, and this is the case of the affine version of those. So we will be studying maps, C-star equivariant maps between such affine semi-projective varieties, and the notion which is key to our discussion is of a very stable morphism. So we will say that such a C-star equivariant map, which obviously will map one of the fixed points of on U to the fixed point of V, we will call it very stable if no other point will go to the origin of the target. So that is to say the preimage as a set of the origin of the target is just the origin of the source. It's only the origin which goes to the origin. And it turns out to be a very useful notion. The one thing you can prove, which is already nice and non-trivial, is that this happens if and only if the map is proper. Of course, if the map is proper, this holds, because then the preimage of any point will be a proper subset in an affine variety. It will be zero-dimensional. So it will actually have to be the origin. So this is much stronger to say it's proper, but somehow this is the notion which will be prevalent everywhere in our examples. So let me just give you the situation which will most of the time appear. We will have an equidimensional situation when U and V will be of the same dimension. We will have V to be a smooth variety, smooth affine variety. And it turns out that for technical reasons, we will have to restrict, or we should restrict to the case when the source is Cohen-Macaulay, some technical assumption. It will help us, for example, to deduce from this property that F is proper between equidimensional spaces, then the map is going to be finite and flat, which is stronger than just being proper. And in a geometrical terms, and that will be relevant for us, this finite flatness of the map will actually be equivalent with the push forward of the structure sheaf on the source being a locally free C-star equivariant vector. So it will be a vector bundle, but as a sheaf, it's going to be a sheaf of algebras. There is going to be a ring structure because we will be pushing forward something OU, which is itself a sheaf of algebras. So there will be this equivariant vector bundle on the base, which is geometrically interesting, and it will play some role at the very end of the talk. But in this generality, I will show you basically three occurrences of such very stable morphisms between affine semi-projective varieties. Before I do that, let me also spell out what it means in terms of the ring of functions, because in one disguise in equivariant cohomology, this is what people usually look at, the equivariant cohomology ring, not its spectrum. And so it's actually just a formulation of these definitions. If you take the ring of functions, A on the target and B on the source, then the C-star actions on those varieties will induce a grading on these rings. And because of the semi-projective condition, the single origin and the positive weight condition, we are going to have only non-negative weights, and the zeros graded piece, which corresponds to the, its complement corresponds to the maximal ideal of the origin, will be just a one-dimensional C, the zero-dimensional piece. And the complement, all the positive weights, we will call A+, the maximal ideal of the origin. And now, in terms of ring homomorphisms, the ring of spectra, F is going to be very stable if and only the homomorphism on the level of the rings is just going to be a graded finite flat morphism, which, it's just a formulation of the geometric stuff. There B is a finite locally free algebra over A. But again, surprisingly, this is the language which appears in a Van-On situation, which will be your first or second example. And in this situation, when you have such a map, there is an interesting algebra which had been studied in all the situations under different names, is what's called the multiplicity algebra of such a very stable morphism between affine semi-projective varieties. So it is denoted by QF. It's going to be an algebra. Geometrically, it's just the coordinate ring of the scheme theoretical preimage of the origin, which I told you was located at the origin. The support is a zero-dimensional, but as scheme theoretically, it's going to be non-trivial, and there will be this algebra, finite dimensional algebra, which we will call the multiplicity algebra. And this actually is easy to understand in terms of our ring of functions. In the source, we have B. We can pull back functions from the base, and we pull back those functions which vanish on the origin, which is exactly the functions in A+. And that's the multiplicity algebra, which has a ring. It's defined like this. Or in terms of algebraic language, we can just take the tensor product of the A algebra B with this one-dimensional algebra over the origin. And this tensor product is going to be the multiplicity algebra. So first of all, the multiplicity algebra is going to be a finite dimensional algebra, which actually the finite dimensionality is equivalent with the F being very stable. And in that case, in this very stable situation, it is actually the dimension of the algebra, which is what people sometimes call the multiplicity of F, either at 0 or in fact, the generic multiplicity over a generic point. The preimage of F will be this many points. So there is now an algebra whose size measures this geometric multiplicity of this map. So very interestingly, this notion, I was really amazed to find. So with Nigel, in studying the Hitchin map, we had discovered this notion ourselves. But then I found that in the situation, in fact, which happens for the Higgs moduli space as well for our project, both U and V will be just Fi space of the same dimension, but you will have some interesting C-star actions on both on the source and the target with semi-projective with only positive weights. And we will study morphisms between them, U and V, which will be C-star equivariant, which in the language of the Arnold school of singularity theory, this is called quasi-homogeneous. They call the map non-degenerate when we call it very stable. Anyway, so this situation, which looks like harmless, so holomorphic or algebraic maps between Cn to Cn, which are C-star equivariant, they studied this in the framework of singularity theory of functions, and they defined this algebra, our multiplicity algebra, they called it the local algebra of F at the origin. And because local algebra is a very loaded notion by now, I have renamed it the multiplicity algebra, which I think is even a more figurative name for this. And one amazing thing they proved, there is this book by Arnold et al. From 82 about singularities of differentiable maps. In that book, amazingly, all this spelled out in wonderful details. They prove, for example, that this ring algebra is a graded Poincare duality algebra. So graded comes from the C-star action as before. So this algebra is always going to be graded, but it's much better than that. It has a Poincare duality. It has a unique Sokol in the top degree, and you will have Poincare duality when you multiply and evaluated the Sokol. And this is all in their book. It was amazing to read this 40 years ago book, now completely relevant to what we have been doing with Nigel. So instead of going and explaining to you how we got to this notion with Nigel, let me start with the new thing, which I discovered now maybe a month ago or so. That in fact, in equivariant cohomology, you find this situation pretty often. You will actually encounter very stable maps, and their multiplicity algebra will be interesting and in fact extremely well studied. So for equivariant cohomology, let me just remind you the construction. It is a construction in algebraic topology, even homotopy theory. So it's actually everything is defined only up to homotopy. So it's a weird occurrence that I will be talking about algebraic topology. We will cook out something algebraic geometric and algebra, and then we will study its algebraic properties. So this discussion could go for any compact group, but up to homotopy, and because we will be doing algebraic geometry later, I will take a complex reductive group. And I recall the notion of a universal G bundle, which is a G bundle where the total space is contractible. And this is called universal G bundle. This thing is well defined up to homotopy. And it's cool. It's very important for the notion of equivariant cohomology. And it has already an interesting cohomology itself. And that's going to be your coefficient ring coefficient algebra. So let's think about this a little bit. So what's the equivariant cohomology of the classifying space of the complex reductive group G? It can be computed from the classifying space of its maximal torus and its Y group invariant part of the cohomology ring. We will be taking all these complex coefficients of the classifying space of the maximal torus. And beautifully, we can reformulate this understanding. This ring is going to be nothing but the W invariant functions on the Lie algebra of the maximal torus and the Cartan subalgebra. And so this algebra will get its grading coming from the grading on T. And then we will be looking at the spectrum of the rings. So the spectrum of this then, just by the construction, is nothing but the Cartan subalgebra over the Weil group, the GIT quotient, which turns out to be non-trivially by Chevalier an affine space itself. So this is going to be our base of our very stable maps. Also, because of the grading on equivariant cohomology, this one will come with a natural cis direction, because the grading, all cohomology will be in degree 2. It actually, we will have a cis direction on the Lie algebra by weight 2, which then will, when you will take invariance, you will have weights all over the place. And this is already going to be interesting. And those of you who have seen the Hitchin system, this is the first similarity. The base of our very stable maps in equivariant cohomology will be an affine space, but with weights all over the place. Okay, so in order to talk about equivariant cohomology, we just take now more generally group G acting here, G just acting to the point. Now we will let it act on any algebraic variety. And then there is the Borel construction, the homotopic quotient one can take using this universal classifying bundle, this contractible space EG. You can make what is called a homotopic quotient, and you will see that what we get, this quotient will naturally fiber over the classifying space for the group. And the fibers you can identify with a copy of X itself. So this thing is this homotopic quotient is a fibration over the classifying space with fibers X. And then what we are going to define the equivariant cohomology will just be the cohomology of this homotopic quotient. Again, everything with complex coefficients. And just by the construction, this will naturally have a map from the cohomology of the base back. And that map, the structure map, is very important. And this is somehow why it's more interesting and more complicated equivariant cohomology. The usual cohomology is because the coefficient algebra is much more structured. There is much more structure. This ring of the cohomology ring of the classifying space will act on the cohomology, an equivariant cohomology of any space. So this, as it stands, this ring algebra is graded commutative only. So the odd cohomology will have a sign when you multiply them with each other. So, but it's still a sort of graded commutative algebra over this ring, commutative ring H star G. And so the crucial notion, which will be exactly what we need, is the assumption of equivariant formality of this action. So this is due to, I think, Goreski, Kottwitz, and McPherson, this notion of equivariant formality. They say the space is equivariantly formal if the Lorentz spectral sequence for the this homotopic quotient degenerates, the spectral sequence collapses, and these there are equivalent notions. It is the same as to say that this as a module over this is a free module, or just more abstractly, this is the free module where you can find the basis identifiable with the ordinary cohomology of the manifold. But this is important to understand. It's just as a module over the base ring, not as algebras. It's much more complicated, the ring structure here than in just this product. And finally, equivalently is the same as if we go over 0 in this ring. Over 0, we will get back the ordinary cohomology of the variety. That's an equivalent for being equivariantly formal. So equivariant formal spaces can be used to understand. That's the point actually of Goreski, McPherson, and Kottwitz. You can use equivariant formal spaces, their equivariant cohomology to understand the ordinary cohomology. Somehow this is a more richer structure in equivariant cohomology, but if you understand this, you can understand the cohomology of the optional space. That's the order of yes, that's their interest. So for us, what if you just see these definitions, it might be reminding you exactly your notion of very stability, and And indeed, it is the case. Equivariant formal, equivariant cohomology of spaces will be a beautiful example of this notion of very stable. So first of all, just a few sentences. When do we have equivariant formality? And in fact, we have several conditions when you will get equivariant formality. One is that if X is smooth and projective and the action is linear, then everything can be reduced to symplectic geometry and Hamiltonian actions by compact groups on symplectic manifolds. And then in Kerman's thesis, she proved that that situation is equivariantly formal and everything is homotopic. So it is okay to go to the real group instead of compact group, instead of the reductive group, etc. Or what we will be even more conveniently assume that there is actually no haute cohomology. And if there is no haute cohomology, then in the spectral sequence, there is no haute cohomology on the classifying space either. Somehow by degree reasons, this is going to collapse. Everything will be equivariantly formal just by this assumption. And this is what we will assume from now on. All the spaces we will look at will have no haute cohomology. That's so nice because it excludes the obvious bad examples, right? If I have G acting on itself from the left freely, then the quotient is just a point. And for free actions, by the definition, you can easily see that the equivariant cohomology is just the cohomology of the actual quotient. Homotopic quotient by a free action is the actual quotient. You would get something extremely small, so it cannot be equivariantly formal. But the issue is that these reductive groups, compact groups, will have an awful lot of haute cohomology in them. So this way we actually easily exclude this class of examples. So anyway, from now on, we assume that everything, and we always know this one has even cohomology because of the discussion about Chevalier's restriction theorem. And this one always has, now we assume that it has no haute cohomology, only even cohomology. Then as a consequence, the equivariant cohomology will have no haute cohomology. And so now we can look at the rings, and they now will be commutative, and so we will be free to take specs on them and look at the affine variety by these rings. Or commutative, also by convenience, we will divide the grading by 2. So degree 2 cohomology will have grading 1 in our pictures. So now the first thing then we note is that the spectrum then of such the equivariant cohomology of such a space is affine semi-projective. It's affine by construction. It's semi-projective because the grading will give us a C-star action, and because the grading is only non-negative, so therefore the C-star action only have only a positive weight, non-negative weights, and because the space is connected, which I should have assumed, H0 is going to be one-dimensional, so therefore there is only the origin in the spectrum, which will be the fixed point of this C-star action. So the spectrum of equivariant cohomology is naturally semi-projective. And amazingly, this notion of equivariant formal is pretty much equivalent or the same as what we have assumed to be very stable. So an example of a very stable map is to take the spectrum of the equivariant cohomology of a topological space or of an algebraic variety with complex coefficients, and over the base, the cohomology of the coefficients, which is this graded ring, whose spectrum is this Chevalier space. So this map is going to be very stable when the space was equivariantly formal. And in which case, amazingly and beautifully, the multiplicity algebra of originally due to Arnold and his school can be identified with the ordinary cohomology of the variety. So there is going to somehow in this story, it is not a mystical thing, the multiplicity algebra. It is the thing actually some people use equivariant cohomology to understand that's the multiplicity algebra in our case. So let me show you an example, which exactly will be the example which show up for the Hitchin system, the case of the Grassmannian, but I will do it in a little bit more generality, and instead of just Grassmannians, we'll look at partial flag varieties for any reductive group. So G again is a reductive group. We will have fixed the maximal torus and the Borel containing the maximal torus. And then we will have some parabolic subgroup between the Borel and the reductive group. So the example to have in mind is GLN for our group G, and this maximal parabolic subgroup, which I call PK, which has this block matrix form. You have K times K block here, and then N minus K times N minus K block here. And you can have any elements here, but 0 in the top left corner. And then if it's invertible, then this will be in our parabolic subgroup. Okay, so on the partial flag variety, which is just this homogeneous space of dividing by P, which will be projective, precisely because it was a parabolic subgroup containing the Borel subgroup. So you have this beautiful, smooth projective variety. You will have an action of G. So G will act on it from the left. For example, in the case of example we have with GLN and the maximal parabolic, we will get the Grassmannian as this partial flag variety. And it's actually super easy to compute the equivariant conology of the partial flag variety just by a little bit of usage of basic properties of equivariant conology. So you want to compute equivariant conology of G mod P. Well, because P acted freely on G, it is the same as the G times P equivariant conology of G, where P acts from the right and G acts from the left on G. But now, because G acts from the left on G, its quotient is just a point. So actually, this is going to be the equivariant cohomology of the classifying space for P. Okay, P is not a reductive group, but it's homotopic to a reductive group, the so-called Levy factor subgroup, which is the quotient of P by its unipotent radical. The unipotent radical is isomorphic as a variety with its own Lie algebra, which is therefore contractible. And so L, the Levy factor, which is now a reductive group, is going to be homotopically equivalent with the parabolic group. And therefore, this coefficient group will be the same as the group which we actually like, the cohomology of the classifying space of a reductive group or a compact or its maximal compact group, which is just then, as I mentioned, you can compute it as the invariant polynomials on its Lie algebra, the Lie algebra of the maximal torus, invariant under the Y group of this Levy factor WL. Okay, this is all just words and a little bit of theory of for general group, but for GLN, everything is very simple. The Levy factor is just going to be, in fact, there is always a Levy subgroup, which is isomorphic with the Levy factor. And this is, in this case, the this diagonal group, I mean, this block matrix where only these two blocks are allowed to be non-zero. We also want this to be 0. Then it is easily seen, it's just GLK times GLN minus K, this reductive group LK. And its Y group then is just SK times Sn minus K. So this algebra, in fact, the equivariant cohomology of the Grassmannian is deceptively simple looking. It's just the invariant polynomials, but with respect to this subgroup of the full Y group. If you had seen the cohomology, studied the cohomology of the Grassmannian, it's not so simple actually. I mean, it's that's why people like equivariant cohomology, because equivariant cohomology looks, and in some sense, it's simple. But what's not so trivial is the map down to the cohomology of the classifying space. So you want to understand the multiplicity algebra of that map, and that's what's going to be not so trivial. Okay, you can, for example, from this, we can see that the odd cohomology vanishes, and there are other ways to see there is no odd cohomology. So at any rate, this is going to be an equivalently formal situation. And then we can now look at this map on the spectrum of equivariant cohomology down to the spectrum of the cohomology ring of the classifying space, which is just T, this Chevalier space of T mod W. And here we just have T mod WL, this subgroup in this full symmetry group in our case, right? In the case of Grassmannian, the Y group is the full symmetry group. And we have this subgroup sk times Sn minus k inside Sn. And this turns out that the map itself is not so simple. So even though these maps are themselves are just vector spaces, the ring of functions are relatively simple to understand, but this map is really where the interesting and non-trivial topology lies. But the message is that looking at the spectrum of equivariant conology of equivariantly formal spaces like partial flat varieties or Grassmannians gives us a large set of examples of very stable maps. And surprisingly for me, I managed to find in the moduli space of Higgs bundles, when one, as I will explain in a moment, we restrict the Hitchin map to an upward flow, we will see basically this same map there. And that will mean that somehow we have the spectrum of the equivariant conology of the Grassmannian appearing in the Hitchin system, which is kind of puzzling. Okay, and just to finish this one, then I just say that, okay, this is very stable because of equivariant formality, and the multiplicity algebra in this story is much less mysterious because it's just the ordinary cohomology of the partial flat variety or the Grassmannian itself. Okay, so quickly now I will recall notions about Higgs bundles on smooth projective curves and a little bit about the Hitchin system. And then our approach will be to study a nice C-star action on this moduli space and the so-called Bialenitsky-Virula theory that induces. So we will be looking at a smooth projective curve at two-dimensional surface with its complex structure. And we will look at the group. For simplicity, we will take to be just GLN. And then we will consider a space which will be, or big space, which is a moduli space of semi-stable rank n and degree d Higgs bundles. It's something natural to look at if you study families of such Higgs bundles, but I will not really go into defining or reminding you what these are. Maybe what is a Higgs bundle though will be more important, so I remind you that. So a Higgs bundle is just a pair of a vector bundle together with a Higgs field, phi, and the Higgs field is just a canonical, a one-form valued endomorphism of the vector bundle. So locally, you should think of the Higgs field as just a matrix with entries from one forms. And with this we can define the Hitchin map. And in order to appreciate the Hitchin map, first I note that the moduli space of Higgs bundles itself has a natural algebraic symplectic 2 form on it. In fact, it's even better than that. There is a whole family of metrics, and the variety has a canonical hyperkiller metric on it. And the algebraic symplectic form is part of the structure. But just looking at the algebraic symplectic form makes us stay in the algebraic category, which is just easier for the presentation. So we have this algebraic symplectic 2 form. And with respect to that, we can study the moduli space of Higgs bundles. You know, in symplectic geometry, first thing you would want to do is to see what are their functions on your variety and what are their Poisson brackets. And it turns out that in this case, we have a full set of Poisson commuting functions on our space, and that is given by the Hitchin integrable system. So for a Higgs bundle, the vector bundle and this one-form valued endomorphism section of the endomorphism bundle, phi, we can just take the characteristic polynomial of this phi, right? This is a matrix at every point of the curve. And because the values are from one forms, the coefficients of the characteristic polynomial will be sections of powers of the canonical bundle. And so that's going to be the values of the characteristic polynomial, or rather their coefficients will live this in the sections of the powers of the canonical bundle. And then when you add them together from I equals 1 to n, you will get what is called the Hitchin base. That's the space of characteristic polynomials. So for any Higgs bundle, computing the characteristic polynomial of the Higgs field, we will get this characteristic polynomial. And that's what's called the Hitchin map, which is has beautiful properties. So first of all, the main reason of excitement that because this will give a completely integrable Hamiltonian system on the total space of the Higgs moduli space. So that means that one thing it means is that the dimension of the base is half of the dimension of the total space. And the second thing it means is that the coordinate functions of this Fi space on M will give us Poisson commuting functions, and you will have, they will be independent, linearly independent, and as many as possible half of the dimension of the symplectic manifold. So it will be a completely integrable Hamiltonian system, and it is actually such a nice and flexible construction that basically most completely integrable Hamiltonian systems of algebraic shape are known to be deducible from some Hitchin system. So it's a very versatile construction, and it gives you a large set of examples of completely integrable systems. So another important property of the Hitchin system is that it is a proper map. As a morphism, it's proper, which, by the way, oops, in our language is just equivalent, being very stable. Well, for this, I have to discuss C-star actions on both of the source and on the base. On the base, actually, the C-star action will be easy. You just act with weight I on the ith component here, but on the source, the C-star action actually is pretty easy to define because it's just going to be scaling the Higgs field by a non-zero complex number, and you take isomorphism of Higgs bundles, and that's going to be your C-star action. And now I can tell you what in general semi-projectivity means for me. It means basically three properties. First, that the C-star action is linear, which just says that you can embed M into a large projective space together with the linear action of C-star on the projective space, giving the original C-star action. That is automatic if the variety is quasi-projective and at least normal, because then you can pull back the C-star action onto a very ample line bundle. But in general, I mean, if it's not normal, for example, there is an issue. So that's the right notion we will need, that it's always embeddable into Pn. Then the second assumption or part of semi-projectivity is that the fixed point set of the C-star action is proper. And the final property, which actually follows, by the way, here from the properness of the Hitchin map, because the C-star fixed point on the base is just the origin. This has only positive weights. So in this C-star action is, this map is C-star equivariant. So anyway, it's going to be over zero, the fixed point component, which is proper. That's called an nilpotent cone. So the fixed point must be proper. Then the last property, which again follows from the properness of the Hitchin map, is that the limit points of any C-star orbit exists when lambda goes to zero. So you take any Higgs bundle in the Higgs moduli space, you scalar multiply the Higgs field, and then you will get a C-star orbit. And in one direction of the C-star orbit at zero, you can close it down. There will always be a limit point. And these three properties, that's why actually we call it semi-projective. In a projective case, you can close it down in both directions. So the usual Bielanitsky-Birula theory considers such situations. For us, we can only close it down into half of one end of the C-star. That's why it's only called semi-projective. But in this case, when this always exists, then we will have very naturally this Bielanitsky-Birula partition of my space into what we call upward flows. So I'm just going to turn this condition into a into a partition. This condition that all the, or this property that all the limit points at lambda equals 0 exist. We will use it that, first of all, the limit point always have to be a fixed point by the cis direction. So we will take a fixed point of the cis direction E, and we will look at all the Higgs bundles whose limit point at 0 will be this fixed point of the cis direction E. And because of this condition, every Higgs bundle will be in one of these things, and in fact, in exactly one of these things. And therefore, you get that the whole space is partitioned by these, what I call upward flows. So these are the Higgs bundles, which are somehow upward from E. So they are in the downward. So E is in the downward flow of F when you go with the cis direction, multiply with lambda, and you go to 0, you get E. So F is in the upward flow of E. So these are going to be crucial, these upward flows, and in a moment I will tell you how beautiful, what beautiful properties they have here. Just I'm telling it now. So this is basically part of Bialenitsky-Birula theory. So I will restrict to the case and everything, or the point we have fixed point is in the smooth locus of the moduli space. In that case, one can show that this subset, those Higgs bundles which flow down to our fixed point E, this upward flow, is going to be a locally closed subvariety. And even better, we actually understand this is nothing but a cell. It is going to be isomorphic with an affine space, but we even have a beautiful model of the affine space. It's just going to be modeled by the positive part of the tangent space at that Higgs bundle E. So we recall that E was a fixed point by the C direction. So at the tangent space, at that point, C star will have some weights, and we will choose the positive weights. And because of the property, there is a beautiful property of the symplectic form with respect to the cis direction. It has homogeneity 1. The positive part will naturally or automatically will be a Lagrangian subspace in the tangent space. And also this vector space will be a model, a non-canonical. This isomorphism is non-canonical. It's a non-canonical model for the upward flow itself. So this, even though it's not canonical, but it's C-star equivariantly true. So we understand this cell with its C-star action up to isomorphism with this model space. And both of them will be Lagrangian in the Higgs moduli space itself. So basically, most of the upward flows, the smooth points will be a beautiful Lagrangian cell, not necessarily closed, it just will be locally closed, but in nice cases, and it turns out exactly the cases that we care about, the very stable cases, they are going to be closed. So let me then give you the definition of very stable, or just say how this is an example of the notion we had started to discuss in this talk. So we will say that an upward flow, this Lagrangian cell, is very stable if and only if the restricted Hitchin map to this. So now this map is between vector spaces of the same dimension. And then you can ask, you have C-star action on both of them, positive weights everywhere. So this is an example from the beginning of the lecture. And so I can say that that map is very stable, which just means, by the way, if you recall the definition, that the preimage of 0 here has to be the preimage of 0 has to be only in 0. The preimage of 0, if you remember here, is just the so-called nilpotent cone, and that says that the nilpotent cone intersecting this upward flow has to be trivial, just the point E. There cannot be any other nilpotent Higgs bundle in the upward flow. That's what very stability means. But because of all these equivalences, we know this is going to be the case precisely when the map is proper, when it is finite flat. So in the case when it's very stable, we are in this situation which I started the talk with. And this is exactly the case when this space inside here is actually closed, because when it's closed, Hitchin map being proper, the restricted map will also be proper. but it is an if and only if statement. This map is very stable if and only if this is a closed Lagrangian cell. So in the paper with Nigel, which we had, not so recently now, but in January, we had put it on the archive. We have, among others, we have classified one type of Higgs bundles, which are among them, which are the very stable ones. So instead of recalling the whole classification, I am just going to give you basically a few examples of very stable Higgs bundles. So first of all, I should say that the notion comes from very stable bundle, comes from Lomon and Drinfeld in their work of the geometric Lagrange program. They considered a vector bundle on a curve very stable if it did not support a non-trivial nilpotent Higgs field. For us, it's the same to say that the vector bundle together with the zero Higgs field is very stable as a Higgs bundle. So that was the source of the terminology very stable. We just generalize this to other type of fixed points of the cis directions. Lomon's main result in that paper was that there exist very stable vector bundles. But here, or in our paper, we found many more examples of very stable Higgs bundles, but of a very different type. When the underlying vector bundle will be a direct sum of line bundles. I'm going to give you examples of such. There is a very important example, the D-canonical example of a Higgs bundle, or even of a very stable Higgs bundle, is constructed as a direct sum of line bundles. Namely, we take the direct sum of the trivial bundle with K inverse up to K to the minus n plus 1. That's the rank n vector bundle. And then we tensor it with K. And then the Higgs field is just the trivial isomorphism from O with the second one, K inverse with the third one. So it's given by this lower triangular matrix. This turns out to be a stable Higgs bundle. We call this E0. It is what we call the canonical uniformizing Higgs bundle. And I'll show you in a moment why it is somehow easily seen to be very stable, because its upward flow is something which actually had been constructed by Nigel Hitchin in much earlier. One of the first papers of his on this subject was the construction of what's called the Hitchin system, of the Hitchin section. So Hitchin system you had seen, but he had then later constructed a canonical, a beautiful section of the Hitchin system. And this is going to where it starts from the canonical uniformizing Higgs bundle. And it turns out that the Hitchin section is nothing but the upward flow from this one. So I'm telling you that the upward flow, which we will abbreviate just to W0 plus from this particular canonical uniformizing Higgs bundle, I tell you first what are the points on it. They are exactly the Higgs bundles which have the same underlying vector bundle. And the Higgs field is going to be the companion matrix of the characteristic polynomial over which we are. So we take a point in the base of the Hitchin system, the space of characteristic polynomials. We take those coefficients and we put it in our companion matrix like this. We take the same vector bundle as in the canonical uniformizing Higgs bundle. And this way, for any point A, we will get a Higgs bundle, which Nigel argues in the original paper, but it's easy to show that they are also stable. And they will give you by construction, the companion matrix by construction has a characteristic polynomial, which is the A you started with. So this is by construction going to give you a section of the Hitchin map. And then you can show that the upward flow, these are in the upward flow, and you can show that no one else is in the upward flow. So this is going to be the upward flow. And because then the restricted Hitchin map is just an isomorphism, then of course this is going to be a very stable map. So this is our first example of a very stable map, is the Hitchin section, which is the upward flow from the canonical uniformizing Higgs bundle. So the second set and last set of examples is going to be a slight twist of this Hitchin section. So instead of just these ones on the diagonal below the main diagonal, we will just change one of them. You recall that these ones were sections, or for a homomorphism from a line bundle to another. We're going to twist just one of them to have a single zero at a given point C. So we fix a point in the curve, and to that and to any choice of k between 1 and n minus 1, we are going to first construct a fixed point of the cis direction by taking the underlying bundle almost the same as before. So the first k terms will be the same, but on the k plus 1 terms, we will, and from on them, we will twist the line bundles by this divisor at C. And that will allow us that when I take the map from here to there, from here to the next one in the k twisted one, I will have an extra divisor, and I can take the canonical section of OC. SC is going to be a section of OC vanishing exactly at C. And that way that this is a slight twist of the canonical uniformizing Higgs bundle. And again, you can show this is stable. So you have another stable fixed point of the cis direction, and then you can wonder about its upward flow. Is it going to be closed? Is it going to be very stable? And this is part of a theory with Nigel in the paper. We prove, in fact, we classify all type 111 very stable Higgs bundles, and then we can in particular show that this is a very stable Higgs bundle. The upward flow from this will be, when the Hitchin map is restricted to it, will give us a very stable map. There will be no other nilpotent Higgs bundle on the upward flow than the EK that we started with. And so now comes the last diagram, which will be slightly heavy, and that will then conclude the talk. This is a computation of how one can compute the Hitchin map on this upward flow. So here is what we would like to compute the restricted Hitchin map of the upward flow. And the way to do it, as we've done in the paper, is using Hackett transformations. So the first thing is to understand that everything on this upward flow can be obtained from the Hitchin section by certain Hackett transformations at the point C at vector spaces, k-dimensional vector spaces, which are fixed by the Hitchin map, the Higgs field at that point. Anyway, that's some Hackett correspondence space. And with doing Hackett transformations, you can convince yourself that this is an isomorphism. And then we just study this Hackett correspondence, and then you can restrict to the point C because nothing really happens outside that point. And then over the point, you have something natural, and which I won't have time to discuss really, but something people had studied. It can be understood by the partial Grothendieck-Springer resolution. And at the end, you can understand this map just as a map from T mod T over the Y group of the LK, which is now we are in that situation of partial flag variety, the Grassmannian, over this. And then what is the upshot of today's talk is that this map is nothing but the spectrum of equivariant cohomology of this Grassmannian. So that concludes the talk. So here I put up my last slide. Here, what is the upshot is that under using Hackett transformations and carefully understanding the Hitchin map on this upward flow, up to some trivial part, this one is gradually quotiented out to something which is precisely the spectrum of equivariant cohomology of the Grassmannian. And then you can then find that the multiplicity algebra of this map is the same as the multiplicity of algebra of this map, is nothing but the cohomology ring of the Grassmannian. And this was where our project started with Nigel, trying to understand the multiplicity algebra of this map. And then I have just some questions. Why do we see equivariant cohomology? And for that, I can offer basically two conjectures or two problems. One is something we are working on with a student, and we can prove it for SL2, which is somehow would explain that in a much bigger situations, we can actually see equivariant cohomology of spaces appearing as zeros of some vector fields which show up in this Higgs bundle story. And the second point to finish with is the original motivation was mirror symmetry, and the push forward of these upward flows should give us the mirror vector bundle restricted to the Hitchin map, which in this case is just an exterior part of the universal bundle. And then having this structure of equivariant cohomology should give us some structure on this universal Higgs bundle. And that's my last question today. What does this mean on the universal Higgs bundle in terms of mirror symmetry? What does the spectrum of equivariant cohomology reflect? So that's it. Thank you. Hello.
Thank you very much for this very nice talk. So any questions from the audience? So maybe one quick question. So is it only the equivariant cohomology of Grassmannian appear, right? Grassmannian themselves, one cannot find them inside the Hitchin model space.
Right, so the Grassmannians were here, but I just didn't really have careful time to talk about these Hackett transformations. So here, when this computation is done, the first step is to understand the Higgs bundles on this upward flow as obtainable from Higgs bundles on the Hitchin section by Hackett transformation. But when you take a Hackett transformation, then you take a k-dimensional subspace of the fiber of your bundle at the point, which is going to be invariant by the Higgs field. So, but those vector spaces will be elements in the Grassmannian of k-planes in Cn, where Cn now is identified with the fiber of the vector bundle at that point. So basically the space of Hackett transformations will live inside this Grassmannian. And the first solution was actually showing that this Grassmannian is the one whose equivariant cohomology then is reflected in this fixed point scheme. So this one here, this Hackett correspondence translated here will be some fixed point scheme. And if that theorem conjecture is correct, then it's always the case that the equivariant cohomology of the ambient space will appear as the fixed point scheme. And that's what I hope will be the answer of why this is the Grassmannian. So the Grassmannian is the space of Hackett transformations at the point. And then that would at least explain why its equivariant cohomology appear. But what does it mean for the Hitchin system? I still don't understand. Or what does it mean for the mirror symmetry is another mystery. But I have been now doing this for a month, and I see more and more relationship. So you can look at literature about spectrum of equivariant cohomology. It is also actually done in 3D mirror symmetry by different means. So it's a pretty well studied area. And those structures, I start to see some of them have the analogs or equivalences for the Hitchin system. So it's a very interesting analogy that Hitchin systems restricted to these Lagrangian flows. And then you think of those maps between vector spaces as some sort of equivariant cohomology. It helps you to analyze it because it looks so structureless, right? A map from Cn to Cn, what could there be? But in fact, equivariant cohomology tells you that it's non-trivial, and understanding such a map, there is a lot of structure there. So
I see. So I'm intrigued by the 3D mirror symmetry that you mentioned. There is an open subset of the entire space that looks like a Coulomb branch of some 3D theory, and there people study symplectic leaves of this space. And I think in some cases, Grassmannian do appear. Are you implying that the Grassmannian observed here can be connected to that story?
I don't yet understand any. I am studying the 3D mirror symmetry from the mathematical literature on it. Mm-hmm. And there is something called the Hikita conjecture or theorem. Yeah, and you are right. The Grassmannian, in fact, it's the cotangent bundle of the Grassmannian which appears there. It would be awesome if our Grassmannian somehow would be related to that, if it's somehow, as you say, some Coulomb branch of something. But so far, I cannot see that kind of connection yet. Also, what's special here, I mean, there it's also beautiful. Hikita conjecture gives you a symmetry so that you take the conology ring of one hyperkiller symplectic resolution, which will appear as the fixed point scheme of the cone on the other side, and vice versa. So that's a beautiful relationship. Yes. But what's different here, for them, this equivariant cohomology at that point is that scheme is in the mirror side. So somehow for us, it appears in the same geometry. So there, the two sides are, as far as I understand, they are not geometrically connected in 3D mirror set, or I don't know if they are geometrically related. So the algebraic geometrical thing, the spectrum of the fixed point scheme on the conic side, it should be the cohomology ring on the other side, but here it's in the same geometry. The scheme for us appears on the Higgs moduli space, and the Grassmannian as well appears as the space of Hacker correspondences. So it's slightly different flavor, but obviously what we do is in the Higgs moduli space, as you say, you know, it's a sum Coulomb range. So I don't know, I hope to see some relationship, as also they have a much larger set of examples, not just Grassmannians. For now, I may see the full flag variety, but I don't yet know about all partial flag varieties. Will they appear in some examples or not?
Yeah, thanks. Any other questions? So if not, let's thank Tamas again for this wonderful talk.
Thank you.
Sure.
There was a question.
Not sure.
No, okay.
So let me stop the recording.